Chemical equilibrium. Hydrogen chloride can be made from the reaction of chlorine and hydrogen. Given the following reaction here, you have the double arrow, so you're at equilibrium, meaning things are happening at the same time. For this reaction K, this is your equilibrium constant. Is 26 times 10 to the 33rd. So this is a really big exponent. This means a very large K. And, excuse me, delta H, the heat, is negative 44 kilocal per mole or negative 184 kilojoules per mole. So the first question says, is this reaction endothermic or exothermic? Well, because your heat is negative, this reaction is exothermic. Then it says, are the reactants or products favored at equilibrium? Well, let's think about it. K equilibrium is the concentration of the products over the concentration of reactants. If you have a very large number on the top, you're going to get a very large K. If I have 2 over 1, my products are greater than my reactants, my K would be 2. So that means products are greater than reactants. Now, what if I flipped that and I had 1 over 2? My reactants are greater than my products. Well, my K would be 0.5. So when my products are greater than my reactant, K is large. When my reactants are greater than my products, K is small. So let's look at the K that we have. It's 26 times 10 to the power of 33. That's a huge number, so this reaction is product favored. Explain the effect on the equilibrium of. So remember that the equilibrium is always going to shift to restore equilibrium. Now it won't say it like that, but it always wants to shift to restore due to Le Chatelier's principle. Increasing pressure by decreasing volume. So you have to think of moles. So if we look at this equation here, I have 2 moles of products on my product side, and I have 2 moles of reactant. So I have 2 and 2. So if I have, we know that volume and moles are inversely related. So if I am decreasing my volume, I'm increasing my moles. However, since they're exactly equal to one another, this particular situation has no change because it's equal moles. Now, if I had 3 moles to 1 mole, then that would change and would go towards the more heavier side of moles. And then it would shift to fixing it. What I mean by that is, let's say, for example, this was only 1, and I am decreasing my volume. Well, if I'm decreasing my volume, I'm increasing my moles. So I go towards the right. Then to fix it, it would shift towards the least amount of moles. Here, because they're equal, there's no effect. Then we have increasing the concentration of hydrochloric acid. So if I increase this, at first I go more towards the right because I become heavier. Then to fix, the equilibrium would shift left or towards the reactants, however you want to say that. Decreasing the concentration of chlorine gas. That makes my right side heavier then because my left side became lighter. So to fix, I have to shift to the left. Increasing the concentration of hydrogen gas. Now I made my left side heavier. I made the molecules on the left side bigger. So you have to think about it like this. Because equilibrium always wants to become restored, those molecules now are going to work so much harder to decompose back to the product, so the equilibrium shifts right. Adding a catalyst. A catalyst is awesome. It provides an extra pathway to get to the end result. It makes it go a little bit faster. It gives you a route of 10 minutes to get to school rather than 30. However, it doesn't affect equilibrium. It doesn't affect the constant, the concentrations, nothing. It just helps it go faster. So this would have no effect on the equilibrium. So you always want to think, whenever it says the effect of the equilibrium, think of what's happening first and then how the equilibrium is going to shift to fix that, because that's equilibrium. What's happening to it, then at that moment, it's no longer equilibrium. So to get to equilibrium, how is it going to shift? For the following reaction of dinitrogen tetroxide to 2 nitrogen dioxide particles or molecules, the equilibrium concentrations at 25 degrees Celsius are the following. Note that it's mole over liters, but don't let that confuse you. That's just big M written out. What is the value of K at 25 degrees Celsius? Is the reaction reactant favored or product favored? So you're looking for your K. So your K is products over reactants. First thing to do is write out your reaction, write out your K. Then you already have so much information right in front of your eyes. So products over reactants. I have my product, which is nitrogen dioxide, and the coefficient, so it's squared, over my reactant, dinitrogen tetroxide. Perfect. I want K, so all I have to do now is just plug everything in. I plug in my product and I plug in my reactant. I have 0.0325 m or mole over liter, however you want to write it, squared over 0.147 molar, and that's not squared. So take that number and you square it, and then you divide by the other number to get your answer. And then that'll come out to be 0.0072. You want 2 sig figs because of the temperature, or even 3 because that's what you used. Either is fine. And your units would be what? Unitless. K is always unitless. Perfect. Then it says calculate dinitrogen tetroxide at equilibrium when nitrogen dioxide is 0.0250 mole over liter. Again, that's just like molarity. So I write out my K expression again. I have K is equal to nitrogen dioxide squared over dinitrogen tetroxide. What am I looking for this time? Dinitrogen tetroxide. That's what I want. I have K because I solved for it in part A, and I have nitrogen dioxide. Then what I like to do is isolate. So you can always imagine it's over 1 and you can cross multiply, which gives you K times dinitrogen tetroxide is equal to nitrogen dioxide squared. So let's just plug in what we got first before we deal with that squared sign thing. I have K, which is I'm not solving for that. I haven't figured it out yet. I'm solving for this, so now I have to divide by K. So I get that dinitrogen tetroxide is equal to nitrogen dioxide over K. I was thinking about the problem below. Perfect. So now you just plug it in. So nitrogen dioxide is 0.0250 squared over K, which you solved for was 0.0072. When you square that and divide, you get that the concentration of dinitrogen tetroxide is 0.0847 molarity. It's a concentration, so you must have a unit of concentration. You can write mole over liter as well. Now it says calculate nitrogen dioxide at equilibrium when dinitrogen tetroxide is 0.075 mole over liter. So I always go back to my K expression to kind of help me visualize what's happening. Products over reactants. And this time, I'm solving for nitrogen dioxide. So I'm going to do this a little bit different just to show you different methods. I'm going to plug in my numbers first this time instead of isolating. So I'm going to say, okay, I know I've my K. It's 0.0072. And then I don't know my NO2 here, so I'm going to leave that the way that it is. Should put that in brackets because that's concentration. And then I know my dinitrogen tetroxide, 0.0750 mole over liter molarity. Well, I can cross multiply which will give me that the concentration of NO2 squared is equal to 0.00054. And then to get just the concentration of NO2, I have to square it, and I get that the concentration of NO2 is equal to 0.023 m. And that is my answer. So it's always just good to know what is K. K is products over reactants in whichever direction you're looking for. Your coefficient is always going to be your product. K does not include solids and liquids, only gases and aqueous. And you can, once you have that information, you can solve for K, you can solve for the concentration of the reactants or the products or whatever.